doesn't wake up, more integral stuff, of the polar funky stuff. And you know what? I finally got the pen to work. So before I say that, yeah. So it does not have Parkinson anymore or tremble anymore. To be honest, I didn't do really anything. Just restart the computer. Funny noises. Anyway, I might have to kind of hop on and off. So what are we doing today? We are doing, there we go. We're doing these. We are doing polar integrals examples. So we're going to be learning, like, I feel that is something that is just important to know anyway. I just don't want to speed up. I want to at least make a couple of examples. Double integrals, triple integrals, and stuff like this. And yeah. So there we go. What do we have? Some examples here. Some examples. And you know what would be ideal to do them in SymPy as well. So actually, anyway, so what do we have here? To compute a double integral in polar coordinates, we rewrite the function in terms of r and theta. Replace dA with r times dr times d theta. Compute the limits of integration of r. Sorry guys, give me a second. I'll be back in a second. There we go. So this means finding the minimum and maximum values of r for each value of theta. Okay, so we need to understand, so just to be, so here's an example, just for this to make sense. So here is just a, we're working just in sort of these 2 dimensions. And so what you need to do is you need to rewrite the function in terms of r and theta, then replace this dA, or which would be dx dy, right, by r dr d theta. What this means is, I'm not sure I intuitively understand this r. That's an important thing to try to understand. Compute the limits of integration of r. This means finding the minimum and maximum values of r for each value of theta. This means is r, like, yeah, so is the radius always the same? You know, what are the bounds, right? R will obviously be always either 0, the minimum, or I guess in this case x squared plus y squared. Compute the limits of integration of theta. These are numbers, not functions of r. So these are actual numbers. And it, typically, I guess they'll just be pi stuff, right? Do the integral one variable at a time. I mean, it seems intuitive. I just don't know how that would neatly translate. How I cannot snap it here? I want to snap this here and this here. Okay. So we have this example here, which is a double integral on x plus y. X plus y. 1 second. So When D consists of all points x, y such that okay, so what a second. What is I'll be back in a second, sorry guys. So, finally, maybe we can get some work done. What else are we doing here? So we're doing, so evaluate the integral. So you're given an integral, but then you're saying, you're integrating a function on an area. So this is actually giving you some bounds. I don't understand why. Oh yeah, okay, so this is just telling you what is the, because I think that is what I'm, that is maybe what I was what I'm missing from the actual quantum mechanics exercise. Sort of understand well the bounds. So this is typically, so what you do is, this is just a function defined on x plus y, but you're saying just the x plus y are bound to these. So this gives you, okay, this just gives you bounds in terms of what values of x and y you can have. So y is always bigger or equal than 0 and smaller or equal than square root of 9 minus x squared, and then I guess that's these, right? We worked this example in the last section using rectangular coordinates. It is substantially easier in polar coordinates. Our origin is the first quadrant inside a circle of radius 3 as shown in the right. This means that our limits of integration are that r goes from 0 to 3 and theta goes from 0 to pi divided by 2. So the function okay, so how is this transformation done? I don't know. I don't care. I guess it's just trigonometry, right? X plus y. Like if you were to yeah, I guess, because I guess this is just, you're saying, so if you want to find x, you're trying to find these here. So you know what I mean? Like I can't paint over, but I can draw it here. I think that's just basic trigonometry, right? So if you have this and then so x is basically this here. This is theta, and so and this is r, right? So yeah, the cosine, exactly, the cosine of this thing is I guess x over I don't I don't remember the basic things. What is the cosine formula? There you go. Cosine is the adjacent divided by adjacent divided by the hypotenuse is which is, yeah, it's exactly, it's x, it makes sense. I could just have pretended that I knew that, and then x equals r times cosine of this. Okay, so that's basic stuff. So this is how you rewrite this, and then and then you just do the double integral. And so let's try to do this. Let's try to do this in SimPy, okay? Actually, let's try to do this in SimPy. See what happens. So, okay, what are we doing here? Too many things at once. Too many things at once. We are now, you know what? I think I should have another file, which is just basically playground.python, and then we just take everything from SimPy. To be fair, I should just probably follow best practices and just it's like as SP, right? Does this work? SimPy as SP and printing. Do I have to? I can't work with so less real estate. I guess I have to do it like these, right? And then does this at least work? Let's say x equals sp symbols x, print x. This is wrong. Undefined np. Oh, sp print. I guess now I have to do it like this. And so we don't care about these. We just say Python playground. What? I can't autocomplete? How I was, oh, I should probably run first. What does this sound? Sorry guys. Did it run? Does it work now? Yeah. How can I get out of this? Okay, so now I do this. Huh? No? Playground. Polyground. Awesome, man. Playground. Okay, works well. So what are we doing? So we want to integrate. We want to do these, right? So let's see what it does. Okay, but why R, right? Let's think about this twice. So why are we replacing? Okay, so I guess what we're doing is, so if first we're doing the integral of these, but we have to multiply by R. Why? Maybe we should go and take a look at some of the theory before. So polar integrals. So in polar coordinates, the shape we work with is a polar rectangle with size constant r values. This means we can describe a polar rectangle as this. Yeah. So in this section, looking to integrate over polar rectangles. Consider a function fr over polar rectangle. We divide the interval into m subintervals of length these and divide the interval. This means that the circles and raise to smaller subrectangles. So we need to find the area. So we need to add all this kind of stuff. Okay, I guess it's times r because you're kind of multiplying by these, right? So this is, yeah, I think so. It makes intuitive sense. So what the integral is doing, if you just ignore these, right? If you just say for a small, first you're saying for a small differential of r, small portion of r, you get that thing, and then you multiply it r times. And so you have one, then you have one section. And then these sections is what you're doing. Basically, you're calculating for each small section of the angle theta. Yeah, that makes sense. Okay. I think that no need to dig into this more. The question is, will this just work as a regular integral? So if I do, okay, so this is a solution. So let's say, let's go and do basically what do we want to do? We want to do, so we have now r, so we have r and t as the angle, SP symbols, and we say r and t. Should probably do this separately and define what each of these are, because it will definitely help. So r in this case, we know that is something between 0 and 3, right? So it's I mean, we know it's real true, positive true, and then t is an angle. I don't know whether you can specify that, but let's see if that works. So essentially, what are you doing? You're doing SP integrate. So the inner integral is basically r times the cosine of t plus the sine of t. Okay, yeah, exactly. Times r again, and so this is dr. So we are integrating these, and we're integrating these on basically the limits are, so this is r and between 0 and 3. So this is the inner integral. So this is like integral 1, and then integral 2 equals SP integrate, basically integral 1, and what you're doing is you're integrating on t, and you're doing it from 0 to pi divided by 2, which actually we've learned that you should probably do it like this. Can I print? Yeah, I mean that's what it is, right? Print I1, print I2. Let's see what happens if we do this. Will this work at all? No. Why? Invalid input. What have I done wrong? So line 8. integrate invalid input pi, okay? Invalid input pi divided by 2. Should I just do it like this? I just maybe cannot give. Oh yeah, look at this. Did it work? Yeah, 18. It worked. So that just, you just do regular you just do a regular integral, I guess. That's what you're doing. Okay. It makes sense. Yeah, it makes sense. Okay. So that's, and I think with, if you do it with if you, now I understand these are now in 3 dimensions, what will be example triple integral polar coordinates. I think it's just a similar thing, right? And cylindrical, sorry. I think I made the same mistake last time. I want an example. Okay. But I guess it's the same concept, isn't it? That's not an example. Triple is uncompleted in cylindrical coordinates. Recall the cylindrical coordinates are really nothing more than the extension of polar coordinates in 3 dimensions. Exactly. Okay, so basically it's the same, but z is z, right? So if we have this thing, but in 3D, right? And now you have these and you have these. Awesome. This is the origin. And so now let's say you have a cylinder. I'm so bad. So a point in here, I mean, yeah, so that's kind of like you have this point, and so this is basically, you know, you have an x component, you have a y component, and then you have like the z component. Z is z. So essentially kind of you have that radius in here, and then here you have 2 angles, so it's kind of the same thing. You have to swipe twice. So, you know, once you're done, if you can follow the same procedure, I guess you do the same thing times r, so you do this, and then you do times theta, and then you kind of go kind of up the 3rd dimension with the other angle. So it's just yet another step. R dz. Huh? dz? Interesting. So first you go dz, then you go dr, then you go d theta. Hmm? I thought there would be another angle. Why do you do that? Why do you do that this way? So so you have ooh. So r times, and you rewrite this like that, but then you do first dz. let's think about these. Let's think about these. So if this is, let's say the just the profile, right? So this is Z, and here you have like Y is kind of coming towards us, and X is here, something like this. And let's say that you have, let's just for a second, let's think about like we have a sphere, right? And so, yeah, X and Y will be, you know, oh, sorry. So X and Y, yes, you will actually have these conversion, but then Z is just that, Z, so that, because that just goes vertical. Sorry guys, I'm messing up with the pen. And so what we're doing is R. So let's say, where am I? Here. First you want to do increments of dz. Y increments of dz times R. Yeah, because that's the radius anyway. Okay, then you're doing with increments of dr. So then you're kind of, what are you doing? So here was easy. Here was really easy and intuitive because it's you're doing dr, so you're doing the radius increments of the, so the sum. It was also not that obvious actually, because you do, if you have the integral blah blah blah, and then it's like r dr d angle. Like why do you have to multiply by r, right? Because this is already the sum over all these little things, right? But why do you have to multiply by r? So that's actually not that obvious. I thought it was obvious, but it's not that obvious. Why multiply by r? And then you do for all the increments of the angle. So this swiping makes sense, these and these. But why you have to multiply by r? If your function is like times r, is it because why r? Why this magnitude? Is it because, so if you're doing the sum of all the increments of r, it means you're doing these r, and you're these, then you're doing these, then you're doing these, then these. I'm not so sure I understand that. Polar coordinates. Double Riemann sum. Double Riemann sum. Double Riemann sum. This is the reason we do this. From single variable calculus, explain how we define an integral of a continuous function of a single variable x on interval a. Include the sketch of a continuous function. For the definite integral in a single variable calculus, this function over a closed calculus eventually develop the definite integral over a closed bounded region. I mean, I think that the Riemann sum is just these. Okay, so this is just this is just the sum that will that it's not yet an integral. That has nothing to do with the r. That's just nomenclature. Where is the r coming from here? So you have this section, you subdivide, and essentially what you want to do is you kind of want to add all these rectangulars, right? So this is an interval of theta, and this is an interval of r, is it? We're looking to here over polar, so consider the function over the polar rectangle, divide the interval AB into m subintervals. What is the interval AB? M subintervals Ri minus 1 Ri. So these are these subintervals in here. So that is alpha. Okay, R and B, these radius. Okay. The length is B minus A divided by M, and divide the interval alpha beta into n subintervals. So this is how to divide the angle. So these are this means that the circles R equals Ri, and raise theta equals theta I for divide the polar rectangle into the smallest subpolar. Yeah, okay, that makes sense. This is what we've done here. As before, we need to find the area A of the polar subrectangle Ri. Okay, so this is basically, oh, okay, so the area of these is, okay, of the subrectangle Rij, and the polar volume of the thin box above Rij. Recall that in a circle of radius r, the length S of an arc subtended by a central angle radius is the length S of an arc subtended by a central angle theta radians is as r times, that's where r comes from probably. Notice that the polar rectangle looks a lot like a trapezoid with parallel sides Ri minus 1 and Ri, and then the theta, yeah, and with the width of the interval of r. Hence the area of the polar subrectangular is yeah, okay, that's why r appears. It's not because of these, it's because of the way you're calculating the area of these little things. So Rij, simplifying and letting these, so we have that, okay, therefore the polar volume of the theme box is with these r star. What is r star? Is r star is the half of these radius plus these radius divided by, so these radius divided by 2. This is r. This is where this comes from, or what? What is a polar volume and why is these? I'm such a problem understanding what is these, the increment of a. Oh god. A is the whole thing, right? I'm just being confused a bit right now. We need to find the area delta A of the polar subrectangle Rij. Okay, this is oh, so this is zoomed in from here. Yeah, okay. This is the difference, the delta in R. Ah. Okay. But then how do we deal with this R star? The double integral of the function f r theta over the polar rectangular region R in the R theta plane is defined as. You still need to find, or is it that these are again just in as in section double integral over the polar rectangular can be expressed as integral as iterated integral in polar coordinates. Hence, I know. So I know this. Okay, so this R comes from calculating the area. But I don't get. You see, the problem that I have here is that we're talking two dimensions, but then they define the function already with. You know, I'm typically just used to the fact like the function has a domain, and so you just give it the radius, and then like this is a two-dimensional thing. So it can be like it should just have one variable here. That's what bothers me a lot about these. Or what? Or am I just, because essentially you're saying, well, if these are inputs, it's like radius these, angle these, and then what's the value here, right? Whatever it is, but like that would be 3D really. So you would be calculating a volume and not an area. You're just saying for radius. If you know that's confusing me. That's actually extremely confusing. That's what's messing up with my head, is the way of defining this function, because you typically have like two dimensions means the function has an input parameter and an output parameter. That's the result of the plot, right? In two dimensions. So I mean, even to the circle formula, but that's H and K. Yeah, well, that is just because that's not a like 2D circle function, right? You can't you know, it's not, it can't just be a regular function, because you have for one x you have two y's. So essentially it's just an equation. So what you're saying is, okay, so maybe this is the way I have to see it, is this is just, you're defining some kind of constraint. So you're saying, please draw all the points that satisfy these, right? But it's really not a function, or at least I don't see that as a function. You know, I think that's what's confusing me. Maybe that's just me using the wrong definition of a function, but this is just saying, give me all the points that fulfill, you know, whatever it is that you're using here. And this is like, you know, these, right? Yeah. So that's the figure. So it's just expressed like that, but it's not really a function, I think. I mean, what's the definition of a function? Because that is not a function, right? In math. Maybe it is, because an expression, rule, or law defines a relationship between one variable and another variable. Yeah, well, from that perspective, that is a function. It doesn't have to be, yeah. There's a relation, right? Between one variable and the other variable. It's just, there's sort of an equation that connects two variables, and that's it. It's just not in the sense of, yeah, that is just really confusing. Because you'd say the function relates this variable to that variable in that way, but this function relates r and theta in a very specific way, which is basically, you know, r and like these, right? And so essentially it comes down to calculating the area of this thing times, and this includes like r, right? And so then you do this dr and yeah, exactly. Okay, so that's where this thing comes from. That comes from calculating this volume. It's essentially the same, right? And here it's probably the same. I think you just have to take that. So it's r. It's probably the same idea. It's just you do first dz, then you do dr, and then you do the angle, right? I guess that's the way that you do this. Okay, just give me a second. So, exactly. In essence, maybe that's also that is also. It's funny because sometimes you just have to clarify your head, like around these more defining things, right, about math. So a wave function in a way is kind of the same. It's a function of, and maybe that is the mistake that I've been doing with these as well, that I've been calling these, I've been saying in the exercise is 4-dimensional because you have one point in space x, y, z, and that is giving you a value, which is not really what it is, right? I don't know. This is actually a messed up thing, right? Because I and it's maybe an inheritance of thinking about functions as like programming, where you have an input, you have an output. That's how you build up the relationship. But then, mathematically speaking, if you think about wave function, it's just a relationship between variables. It doesn't have to be such a linear function, right? It can be something kind of funky. So how these things relate. And so a wave function is a function of, say position and time, right? And so you're relating these variables, but it doesn't have an output per se. It just tells you how does the position behave over time. So you have to think of it as not as a linear function, but as a generic kind of function. This is something that, like, it definitely makes it seems stupid and new, but it's an important thing. It's an important distinction to make, because then it means that the exercise, it is indeed just a three-dimensional thing, right? But essentially you do the same. So I'm just not gonna do these. It's I guess the same. The R kind of comes from the same here. It's like you do R times. So this is basically the volume. It's kind of like, I guess this is the volume of the thing, and then you do dz, and then you do dr, and then you do, it's like an extension of that. So it's the same concept. So you have is the region that lies below the plane z equals x plus 2 above the xy plane between the cylinders so here you have like this volume that is expressed by this relationship, and then you just have to find the bounds. Let's put it this way: you just have to find the bounds, and that's it. And I think we have to, and that's how we have to solve the exercise. It's a triple. It all boils down to finding the bounds and then kind of doing these, right? So this substitution of, well, it's not substitution, but you have the function, but you have to remember to do times, to multiply by r when you're doing the integral. And I think that is what one of the things that I was missing, maybe. Let's see. So I'll try to approach it like I think I have. I'm still feeling maybe not super comfortable not having a full understanding of making sure why the R works, but I think I mean if I assume, and I think that's a good assumption, is this comes from the sub area calculation or sub volume calculation, and then the order of the integrals just makes sense. It's like you do dr d theta, or dz dr d theta, and then off you go, and that's it. But what kind of like is bugging me in my head is this kind of mistake. There's such a fucking basic mistake of like thinking of the function is like saying you have this a point in 3D space, and there's some. That's not what it is. A function is just a relationship between variables. That's what it is. It just happens so that sometimes you can express these as a linear relationship. Maybe not linear, but it doesn't have to be linear. Linear not in the sense of linear, but in the sense of like one of the variables is kind of independent. Not independent, it's like fully just, you can isolate the dependency and say, well, y is equal to, these, right? I mean, you can always do that, right? You can always do that. I mean, the expression of a circle is just, if it's like x squared plus y squared equals 16, right? You can always say, y is like, yeah, why not? You can always write it like this. Of course, you can always write it like that, but we don't always, we don't have to. And so this is just a way to say, well, this is an expression, right? A function of these variables. There's a relationship between these variables. Whether you write it as a function of theta or r is your choice. It just bothers me sometimes you have this like f of x, right? And so you're saying, well, f of x is like, x like just the assumption that we make sometimes, the simplification of like saying, you know, f of x equals like, you know, whatever it is, and then you're like, you just think of these as one dimension. It's not, it's two-dimensional, right? It's really two-dimensional because this is actually saying y, you know, whatever it is, like, so this is what you're doing. It's just that this happens to be expressed as a function of x now. It's stupid. Anyway, that's definitely stupid. It just feels idiotic in a way. Really idiotic. It confused me for a while because of, you know, it says consider the function f r theta, and I'm like, okay, but then it means r and theta are the the inputs, and then there's a third value, but it's not really. For some reason, I always assume when you write something like that, and it's probably the 5th time I say that, I just have to convince myself somehow. Does not necessarily mean that there's a third dimension, like that this is, it's a function f that has two dimensions, r and theta. And so in this case, right, it can have x and y, right? You have this kind of complex equation or set of equations to define this, maybe, but you can yeah, of course you can express x as a function of y, and sometimes, you know, you might have two solutions, and that's fine. That's why you have a square root of, or squares or square roots of, and stuff like that. Yeah, why not? Of course. But then it's yeah. So in the actual exercise, here, function of, so time is 0, so we're ignoring time, so it's a function of just x. So yeah, you see, but that's what's bothering me here. This is more like, in this case, there is another variable, isn't there? That's what bothers me. Like, is this a way? What's the way of expressing that? Is it that you're evaluating? There's definitely, like, you know, theta is missing here, right? That's my point. Although it's assumed that it's just 2 pi, right? Because it's the full 3-dimensional space. And so it really just, the values just depend on r. So, but there's a value involved. Like if you just give me r, I'll give you a value, right? That's my point. Is that's anyway, I have to refresh myself, I think. Just kind of disconnect for a while. See you next time. Making some progress though, slowly.